Hey everybody, it's a rainy day here in Mobile, and the sound of the rain is beautiful. I thought I would make it even more beautiful by doing a real fast tutorial, a very first step tutorial. So I'm going to do 3 iterations here of this same or similar program. The first program's only going to count from 1 to 10, printing tick each time. So tick 10 times. This will be a version that's Linux only. I've put in a little bit of the boilerplate. Code has to start at an even address, an address that is a multiple of 4. So this is a directive that says power of 2 alignment, and it's 2 squared or 4. Power of 2, so the 2 is the exponent, power of 2, so it's 2 times 2. That's an alignment of 4. The next directive says I'm writing code right now. The directive down here is what follows. This is data, and then finally I have .end. Okay, so the next directive I'll need, and remember this is Linux only, is global and main. So now I will have main, and I know that the last thing I'm going to do is a return. Let's see, I'm going to come down here and add my data because it's an easy time to do that. So I'm going to say this one is tick, and another assembler directive. Oh, look at that. Maybe I should move everything over just to make it pretty. Alright, and select these and go like that, and presto, everything's pretty. So here's tick. Another directive called ASCII Z. That says I'm going to give you a null terminated string. So ASCII for the ASCII character set, and Z for null terminated. And that's going to be tick. I don't need a new line. If I did need one, I could just put it right in there. I'm not using, I don't have a need for a new line because I'm going to be using puts. Alright, so the very first thing I need to do is to back up the X30, as we talked about in class. X30. Now I'm doing one 8-byte register, but it doesn't matter. I still have to increment the stack in units of 16. And now that I've done that, I'll shift right down and undo it. And this way, if you undo what you've just done, you will not forget. So this is going to put back the value of X30 that main entered with, and notice the different syntax. So this is going to be the syntax for pre-operation, and this is the syntax for a post-operation. So in this case it's negative 16, so it's a pre-decrement, and over here it is a positive 16, so it's a post-increment. Alright. Now if I were to compile this right now, or really assemble it right now, I'd have a working program. Next thing I'll throw in is main can only return one thing in this, this project. This is a simplification. So values are returned from functions in the 0 register. So I could, instead of an X, since the signature of main is int main, I could say W0 with WZR as what's being loaded. So here I'm going to return 0 from main. Okay, what's my program supposed to do again? Count from 1 to 10. Printing tick. Okay. I'm going to need a way of counting. So I'll use a register, of course. And what kind of register is it going to be? I'm not talking about X or W. That really doesn't matter so much in this case, but what I do mean is, will it be one of the scratch registers or one of the non-scratch registers? Now here's the thing. The decision between the scratch and non-scratch is, am I going to make a function call from within main? The answer is yes, because I'm going to be calling puts. So therefore, I need to use a register that will not be broken by making a function call. So I'll just pick one, x20, and manipulate the stack in a pre-decrement of 16 bytes. Make sure to balance that out with a post increment going back to x20. So that's done in this way. But look at this. I'm doing 2 stack pushes and 2 stack pops of a total of 32 bytes. And I do have an instruction related to STR called STP. So I'm going to switch over to using STP. I won't need this at all, and I'll add my x20 here. So now x20 and x30 are going to be backed up, and I can get rid of this and put in my x20 here. And be careful to change the LDR from one register to a pair of registers. Okay, now I can put into x20 my counter. So I'll start with 1 since I want to count for some reason from 1 to 10. And I'm going to then add a label. Now this is a temporary or ephemeral label. It's just digits and a colon. And I encourage you to use this because the temporary labels can be repeated over and over and over again. Whereas the labels that are symbols like that, main for example, you only get to use once. So you're going to need a lot of labels, and you'd spend a lot of time coming up with creative labels just so that you don't repeat them. But the temporary labels you can repeat over and over again, and there's a pretty ingenious way that it tells unambiguously which temporary label, let's say you have multiple ones, so which one of the ones you mean. So here's the top of my loop. I'm going to compare. Let's see, I'm going to compare x20 to 10. Maybe since it's 1 to 10, then I'll test for equality, so to 11. When I get to 11, I have to stop. And so if I get to 11, branch equal to the bottom, so let me put in another temporary label. So 2 forward. Okay, so I'm going to go over here, and this is 2. So this, just to complete the label discussion, this to go back to the 1 would be go to 1 backwards. So you see how it's unambiguous. The 2 that I mean is the one, the closest one that comes forward. And which one do I need? I'm going to go to 1 backwards. Alright, but I need some more code. I need to load the address of the string. Now in the Linux only version, You would do that using a load of a register, and the signature of puts, well, let me put the comment over here, is, I'm going to ignore the return value, so it's going to look like puts char star. So hence I need to load an X register. How do I know it's an X register? Well, it's a pointer. And which X register must it be? And that would be the first parameter goes in the first register, X0. Okay, so whoops. I use too many keyboards of different key spacings and it really screws me up. Okay, so into X0 is going to be the address of the label tick. And then I'm going to make a function call, that's BL, to puts. Finally, I better increment the counter, otherwise it's an infinite loop, and that would be add. The destination is x20, and the operands are x20 and 1. Now folks, you can't do putting in literals there willy-nilly. There are limits to the types of literals that you can put in there into any instruction. Remember, and why is this? Remember that all ARM64 instructions are 4 bytes. So into those 4 bytes has to be everything that the machine code knows what instruction it is, what the operands are, and the literal. So there must be a limit on the size of literals that is less than 4 bytes. Okay, so let's see. I am going to stop when x20 it reaches the value of 11. So that means 10 ticks. I'm loading up the address of the string, calling the function, adding 1 to the counter, and branching back up to the top. Let's see if this works. And I'll just go here. What operating system am I on? PWD. Oh, I'm on the Mac. That's too bad. Well, this is going to work. I'm pretty sure it's going to work. So I'm going to go ahead and start coding the one that is compatible with Apple and Linux. Okay. To do that, I must include my macro package, which was a lot of fun to write. And in fact, I'll make the text a little smaller so that I can show you the macro source code as we go. So Apple Linux convergence .S, and let me open that. Okay, that's kind of silly. I'll put that here and open that and drag it over, and I'll drag it over, and I'll drag it over and over, and screw it, I'll start over. There. For some reason it wouldn't drag over. Okay. Very good. So now that this code is included, let's begin using it. The first thing, the first change is how main is declared. And the reason is on Linux it's main as you see it here, but on the Mac it is slightly different. So I have a macro called global label, glabel. So I'm going to replace this with glabel, and it's just going to be main. And on the Macintosh, it'll be global, .global with the label, but a prepended underscore. And on Linux, it'll be global with just the label. Okay, very good. And then instead of this, I'm going to use main. And notice there's no colon there. Maybe I should have left that off. But looking at main, you'll see that it's underscore main versus no underscore main. You know what, maybe there's a better way of doing that. Okay, but this is the way it is right now. The next thing, I have a shortcut because this sort of thing is done so often. I'm going to do this. Push pair, and the macro, I'll specify which pair of registers to do, but the macro will fill in the rest. Let's take a look at that. Oh, it's push underscore P. Glad I looked. Remove a space. So you see how the macro, push P, A and B, will do a store pair of the first register and the second register, followed by a pre-decrement of 16 off the stack and putting it into the memory. Down here I will replace this with pop pair, make my indentation line up, and then I can get rid of this. The Macintosh likes the use of start proc and end proc. Linux, if you have it, great. If you don't have it, great. But Mac really wants this, so I'll put it in. And it says after the starting label. So here comes, there's the starting label. Let me put in start proc. And after the return of a function, and this would be true for every function you write, after the return would be end proc. Now, the next difference is how the addresses of labels are loaded into memory. Okay, so on Linux, it'll continue to be the LDR into a register with equals and a label sign. But that actually uses up some additional memory that's not completely necessary. The Macintosh does it differently, and that's using my local load address, LLD, local load address. And so I'll replace that line with LLD, local load address, and I want it to go into X0, and the label will be that without worrying whether it is a underscore or not underscore. In fact, only on the global symbols you'll need in function names, etc. You'll need the underscore. But let's take a look at how Macintosh does it. So remember that what am I going to say, folks? Every ARM instruction is 4 bytes wide. We know that the addresses are in theory 8 bytes wide. So how would you have one instruction that loads 8 bytes and fit with an 8-byte address that fits in 4 bytes? Can't do it. So what Apple does is they break it up into two things. So here is the page number. What is the address of a page? And so it goes and finds the 4 kilobytes, so that's 2 to the 4096, so it's 2 to the 12th. So 2 to the 12th is getting here. So the high order 12 bits of the address are put into the register, and then added to the register are the low order 12 bits. You'll notice that altogether this address is limited to 24 bits. No, am I saying that correctly? No, I'm not saying that correctly. Because the page address will be all of the high order bits. Am I saying that right? No, that's this is what I was referring to. One of those senior moments, folks. So this is for labels that are relatively close by, and by relatively close by I mean within many megabytes away from this code, because you are getting at a 24-bit address here. So I did a local load address of tick, and I called puts. Ooh, but wait a minute. Is it underscore puts or is it not underscore puts? Well, I have another macro for that. Call the C runtime. Call the C runtime and just use the symbol. Alright, I think that's all I'm going to have to do. So this is the version that'll work on Mac and Linux. Okay, so GCC, let's see what mistakes I left in. Now, the first time on the Mac that you use a program in a while, it'll take longer as it sniffs to see if there's any malware. I bet if I run this again, it's going to be fast. So, okay. Now, what did this produce? There's the executable, a.out, /a.out, and how many ticks did I get? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I declare this program a success. Okay, so we're up to here, and now let's move on to the... Come on, stop that. Stop that. What the hell? All I'm doing is left clicking, and it's behaving like it's a right click. Let's see if I click over here. Yeah, that was weird. All right. Let's make an improvement, and we'll do a third step, which is if the value is even, we'll do a tick, and if the value is odd, we'll write talk. Okay, so what am I going to need to do that? I'll need some extra instructions, obviously, and I might need some more labels. So maybe my choice of 2 here was a bad choice, because the label that I'm going to want is going to be in the middle here somewhere. Now I could give it an arbitrary label, like 91, just pull something out of the air. But I'm going to want to make it pretty. I'm going to make it ascending order. Something that I customarily do is notice the branch here is leading to the instructions that lead on the way out. Okay, so what I'm going to do instead is rename this by convention 99. So when I know that when I branch to 99, it's going to be the code that leads directly to the exit. Okay, so if I have counted all my loops, I will branch to the exit. All right, now I just need to figure out whether or not the value is even. And let's see. There are different ways of doing that. I might AND into x0, x20, what am I ANDing? I'm going to AND x20 and 1. So if the AND results in a non-zero, it was odd. It means that the 0th bit was on, so it's an odd number. There are other ways of doing this. There's an instruction that is a bit test. So I could say if an arbitrary bit is on, so that's going to set the, okay, so I'm going to put in, there are other better ways of doing this, but this is the simplest conceptually. Now I'm going to compare x0 to 0, but there's a way, when it's either 0 or non-zero, there's a shorter instruction. So compare and branch if non-zero. Okay, and that's going to be to, let's say, I'm comparing x0, and if x0 is non-zero, I'm going to go to, let's say, 10 forward and grab a drink with Guinan and all the great people in Star Trek. So if I get here, watch what this, how I write this comment. It's when I get here, x0 is even. Okay, this kind of comment is especially useful. Okay, rather than test x0, it's coming before. Instead, I'm doing this after, and it says when I get here, this is what I know to be true. Okay, so if I'm here and I have found it to be even, I want to load up the address of tick. And then I'm going to branch to, I could either print right here, but then I would have two calls to puts. I can eliminate one of those calls to puts by saying branch to 20 forward. And you'll see what I'm going to do here. This is going to be 20. And here is 10. And that will, if it's not even, it must be odd. So local load address of x0 and talk. And then it's just going to fall right into the print. So you see, if x0 is even, I load up the even string and branch to the print. If x0 is odd, I will branch to loading up the odd string and fall right into the print. Okay, speaking of the odd string, dot ASCII Z talk. Okay, now let's try it. Okay, GCC and /a.out. And ooh, I have talk tick. So why is that? Ah, yes, I remember that my first value is 1, not 0. Okay, so this is actually the correct value. Odd, even, odd, even. Okay, I hope you have or will find this useful. And I'll draw the video to a close now. Thanks.